Okay, well, we're very pleased for our second talk of the day to have Charlotte Chan from the University of Michigan, who will tell us about generic character sheaves and parahoric subgroups.
Thank you very much to the organizers for this for inviting me to get this talk. Basically, the talk will be a bit of an overview towards some developments towards an explicit geometric model for a representation theory of p-adic groups, and that's essentially representations of so-called positive depth. I'll tell you more about what that means later. And these kinds of objects are really central to the Langlands program, and so that's so the goal is to, let me just write down what I said. Overview. That was it. Towards the explicit geometric model of a representation theory, abbreviated by RT, of p-adic groups. And these kinds of objects rose to a new level of fame on September 24 of 2021 in Apple TV Plus's release of episode 1 of season 1 of this TV show called Foundation, in which they had a famous actor say to the tens of millions of viewers, maybe which included some of you, but based on the looks, none of you are watching it. But this protagonist says, ring of integers of non-Archimedean local fields. So this is now, many popular, yeah, so it's really popularized this subject. And now the backing of Hollywood, we pursue this with renewed gusto. And whenever I say p-adic, I actually mean non-Archimedean local field, with which now tens of millions of people know non-Archimedean local fields. And let me tell you what this means. So in Melanie's talk, we had a number field, extensions of Q, and then we also had the function field analog, and the non-Archimedean local fields basically split into these two camps as well. And so on this side, the local version of this object is QP, and so that's where p-adic comes from. But we also, I also loop the things over here, which technically aren't p-adic, into this situation as well. And so the analog here is I take Laurent series, which means that I'm allowed to also have negative, this is the set of all things that look like this, a, I, t to the I, where I is allowed to be negative, but it has to stop somewhere. Okay, maybe like this, that's satisfying. Okay. So they also said ring of integers in this TV show, and those will be important for us as well. So in here, these are the p-adic integers, and so these, this is a closed unit disk inside here. And then inside here, the analogous thing is where you take all of these things that don't have negative exponents. And so I won't talk about this row here, but these two rows will be really important, as they were in the TV show. Okay, so today in particular, I won't talk about the entire category of representations, but only focus on a particular class of representations inside here. And these are called supercuspals. And these can be defined in a number of ways. You can say something like the matrix coefficients are really well behaved, they're compact mod center. Or you can say something like the Jacquet functor is equal to 0, but whatever. Let me tell you why their role in the representation theory. So the point here is the following fact, is that any, let's say, smooth, irreducible representation of a p-adic group appears in the parabolic induction of a supercuspal. And so, in some sense, these are like the atomic atoms of whatever complex molecular structure is going on, right? These are really the kind of the things you need first before you begin to understand everything else. And so let me tell you the relative difficulty of the terms in here. So parabolic induction is a well-known construction and representation theory. It has a very explicit formula that I'll later tell you about in a finite case. And so we consider this this construction to be easy. The sense in which any irreducible representation appears, the word appears is in fact very difficult. So this is hard. And the class of supercuspals, that's also kind of hard, but it's less hard than this one. So I'll call it medium hard. But it is our first task before we understand the rest. So that's where we're everything will be just about these objects here. Okay, so let me tell you what they look like. Okay, so an example of a p-adic group is something like SL2QP or SL2 in the local function field setting is equal to this thing. So often
P not equal to P.
what?
Do you assume P is all? Or
I haven't made any such as
it works for people, everything you're gonna say.
everything I'm going to say. Well, everything I'm about to say does. Yeah.
And the sense of difficulty is in the geometric setting. You don't mean classical.
I mean, like classically, we don't know how to parameterize all of these things.
But appears is not hard classically.
So it's I mean, there can be many things that appear. To understand each individual thing is hard.
Okay, that's what you mean.
So here's the simplest recipe is the following thing. And it takes on the structure of this over here. Is that is first I'm going to let take a representation pi of SL2FP. This is a finite group. Seems like a reasonable object. What we have is a surjection from SL2QP, oh sorry, CP, or SL2FP T to SL2FP. And so in this case, this is just taken by taking P to be equal to 0. And in this case, it's just by taking T to be equal to 0. So that's the map. And what this means is that if you have representation, in other words, some vector space on which this thing acts, then you can pull back that action along this surjection. And so you can naturally view that representation, our representation pi, as a representation of this much bigger group, right? This is an infinite group now. And then the third task is to do a compact induction. And anytime the word induction comes up, you should just say, I mean, this is some kind of averaging process to get obtain an action of a bigger group on a possibly bigger space. Usually a bigger space. So I'll just write this as compact induction. 3 should be viewed as easy. 1 is hard and 2 is also easy in this recipe. So how do you know you've gotten a supercuspal? If this resulting thing is irreducible, one can check, and this is a nice exercise, and it's kind of a general fact, then it is supercuspal. Okay. Okay, in this case, this kind of representation that gets popped out is called depth 0. And what this is measuring is the fact that you came from something on SL2 FP. You came from something where you mapped T to 0. Okay. So now this notion of depth, another way to say it is it's saying it's measuring how much you have to shrink a subgroup of this SL2QP before you find a fixed vector. And so you can think this depth is measuring the complexity of a representation. You know, if this depth is really small, that means that actually your compact open can be pretty big before and you can find a fixed vector. If this notion of depth can be positive, so let's say if it's like 100, then you have to shrink the subgroup of this one much further before you find a vector inside this representation which is fixed by it. So you should think this depth R is a bit like measuring complexity of a representation, like in the linguistic sense of complexity, not like computer science. Okay. So how do we get positive depth? Yeah.
Just a question, sorry, that just maybe it's really basic. I just want to make sure, you said, did I understand that you said that 1 is hard?
Yeah, one is hard in the sense that that it might not be easy to construct what this representation is, even though it's just of a finite group.
There's a particular one you're looking for?
No, just any one such that the induction is induction is irreducible.
It's hard to do 1 so that you.
So that, yeah, that's right. Yeah, that's right. So for example, what's the easiest representation you could take? It's a trivial representation. That's not a hard thing to do.
Okay.
But if you feed this in, the resulting thing will not be irreducible. Yeah, so let me say a bit more about this. So I will not say more right now. I will say more later. Yeah. So here's so this problem of constructing supercuspals has a really long history. Maybe starting in the 70s or so, people constructed these objects for GLN, for example, and then inner forms of GLN. And it was some time before people had any sense of how to do this for like general G, drop the L in the N. So I think the first case in which we have a really, okay, well, so some for general G, here are some important milestones. Is the work of Moy, Prasad, and independently Morris. And basically what they do is understand this step zero story. And then Adler was the first person to have a positive depth construction of these objects. And then this was vastly generalized by you to give what is today the most general construction of these supercuspals. And thanks to work of Julie Kim and Jessica Finson, we now know actually, at least in good characteristics, so for all but finitely many p, this last bullet point is actually exhaustive. Everything can be constructed in this way. And so let me tell you about what this construction looks like. So it goes by doing the following thing. You boost step 2 by, instead of doing this simple thing where you just take this t goes to 0 map, you replacing with an algebraic construction. So I'm lying a little bit when I say this, so let me slightly qualify this lie. So this depends on some data about the group. And so let me give an example for GL8, let's say. So I'm trying to get up to something like GL8 of, let me write FP prime T. This. And the method goes, well, inside GL8 of FP prime T, I have a GL4 of an FP squared prime T. And that's like, you can think of this is the analogy, like this is an analogy with like how C star sits inside GL2R. And inside here, you can, for example, take GL2 of FP to the 4. So notice here that the field that's being input is changing, right? It got larger as your group got smaller. And that's part of the complexity. Okay, and so what you could do is you could take this group over here, perform 1 at this level, and then kind of do a process in order to get to this level, and then perform something else here, and then go to the next level, each one in algebraic formulation. Here's a geometric way, I'll call this algebraic, right? And this is the motivation to everything I'll say today, which is that to get positive depth representations without going via this algebra, I could instead say, well, maybe I want to keep 2 to be this really simple recipe of just sending t to 0, but maybe I'm allowed to only send t squared to 0 or t cubed to 0. And by doing that, I've introduced complexity in step 1, but I've kept everything else simple. Okay, so here, the geometric way is to boost 1 by replacing SL2 FP with, say, SL2 CP mod P squared or P cubed or P to whatever. And then in the function field setting, this. So just for normalizing purposes, I often put a +1 here, and that's so that when R is equal to 0, you get depth 0. Okay. Are there any questions at this point? Okay, so so the main takeaway from this talk will be the following thing, is that use algebraic recipe is geometrically simply parabolic induction. Okay, so this is the thing I want to explain for in the rest of the talk. Any questions about this? There's some things we have to adjust to make this literally true, but this is the. Let me leave it like this. Actually, I don't want to leave it like this. So let me start with a little bit of representation theory. Let me tell you about the simplest case of parabolic induction. And I'll tell you about it for, let's say GL2. Inside GL2 FT, I can consider the subgroup of upper triangular matrices. And what I can do is there's a natural surjection from this upper triangular stuff to just the diagonal stuff, just by forgetting the upper right corner. And so that means that, I mean, this is an abelian group. This has really some easy representation theory. If I take a character theta of this diagonal piece right here, I can view it as now a character of the upper triangulars, and I take induction all the way up. We call this parabolic induction. So it's basically saying you have an induction from something like upper triangulars, but the input from upper triangulars is really a diagonal input. So I'll give you the definition. This is the set of all functions on this finite group, satisfying a nice equivariance property, which is the following. It's for any G inside GL2 and B inside this here, these functions must transform under right multiplication by B in this prescribed way. Okay. So this is a very explicit thing we have here. And in representation theory, at least for representation theory of finite groups over in characteristic 0, we know that the representation theory is completely determined by its trace, by just simply the class function associated to this representation. So let me tell you about the class function associated to this. The class function associated to this, you can just compute, and I'll tell you the answer. This is the set of all things, and I'll call this B of FP, HB of FP inside GL2 FP, B of FP, such that H inverse GH is inside B of FP. Since HG inverse H is in B of FP, that means I can apply projection to it and then apply theta to result. So that is explicitly the trace of this, this map here, this map to GLN. Okay. So I should say that this isn't a GL2 specific thing. You could have just simply erased the L and the 2, and then it's exactly the same. So I want to somehow bring algebraic geometry into this picture so that I can tell you about this. So I better tell you what parabolic induction means geometrically. And so in algebraic geometry, a really general thing that we have is something called sheaves to functions correspondence, which tells you that if you have some nicely behaved sheaf that has some equivariance under Frobenius, then you can take the trace of Frobenius, and this gives you a function, sometimes a class function. In our case, it will be a class function, and in general, it's just a function on the FP points. So in this case, okay, so and especially this sheaves to functions correspondence has some really nice behavior. It basically says that any, like, any reasonable geometric thing you do over here has a reasonable reasonable function theoretic analog. So for example, you take a pullback over here, what happens to the function? It's simply a pullback. Okay, important for us here will be what happens when you do a push forward. When you push forward, then what happens in terms of the function is you take an average over the fibers. And so under this, we should be able to cook up some kind of algebrogeometric object whose trace of Frobenius looks like this one. So let's do that. So I have a theta of this thing, that's a pullback. So my theta thing is living on T. I want something on GL2 of FP. So I'm gonna push to this. I'll just put the L in the 2 here. Okay, and so let me figure out what these maps are going to be. Well, I want the fiber over any G inside here to be this thing. So I'm going to just write down what that is. So I'm going to write down all things G, comma F, HB inside G times G mod B, satisfying this property right here. H inverse G, H is inside B. So when you take the FP points of this fiber, you exactly get this indexing set. Okay, so I'll call this map pi. This map pi just maps this pair to G, and this map maps it to this inner right here, the projection of H inverse GH. Call this F. Okay. So what's the algebrogeometric analog of this thing is, well, on T, there's a version of theta that you can take. Those things are called local systems, and there's a multiplicative local system, as in it satisfies some nice property under pullback into the multiplication map on T. And so you can just let's, for the sake of this talk, just think of this theta and this L theta as just being the same. So I can start with this L theta now, and I can do something to it. I first pull back under F, and I push forward under pi. This thing is my new parabolic induction. It's called the same thing as over there because in this case where we took the diagonal torus inside here, everything agrees. Okay. Now, the issue becomes that if you were to take one of these representations and put it into step 1 of the recipe, the resulting representation, compact induction, is not irreducible. So none of these guys actually give us supercuspals. Okay, so where are we getting supercuspals from? They come from the following thing. So let's take GL2. So inside GL2, we of course have this guy in here, which is isomorphic to FP star, cross FP star. And this is a torus. And what a torus to me means is that over some extension, it becomes a product of GMs. So it becomes a product of FP stars. And in this case, it just on the nose is a product of GMs. But there's something slightly fancier that you can do, which is GL2 over FP has a torus that that only becomes a product of GMs over degree 2 extension. And this comes in the following way. This thing here, GL2, this is the same as taking FP linear maps on FP squared. And certainly an FP linear map on FP squared is simply multiplication by FP squared on itself. So that means that inside here is sitting an FP squared star. These two things are not the same, which one can check, for example, by calculating that this has size p minus 1 squared, and this one has size p squared minus 1. So they're not the same thing. And the point here is that even though this thing is not a product of GMs over FP, it is over FP squared. And that's the benefit of using this algebrogeometric thing over here. So in this world, everything is somehow I'm allowed to pass all the way to FP bar. And so that means that all the objects over here can still be defined because I still have this thing that's becoming a product of GMs eventually. So I guess one can think of this as capturing the eventual behavior as you go up field extensions. But somehow it also remembers something about the FP behavior. So let's figure out what happens over here. So by figure out, I mean, I'll tell you, it's not an easy thing to figure out. But so the representation theory of GL2 FP splits into two camps. We have the ones that are associated to this diagonal torus. So these are given by parabolic induction from B of FP to GL2 of FP of a theta. And the second thing is by something called Deligne-Lusztig induction. Deligne. Induction. Which goes like this. So in this case, in this GL2 case, one can consider the set of points or the variety defined by the equation x to the p y minus x y to the p is an element of FP star. And one can calculate that this thing has an action of GL2 FP. And it also has an action of FP squared, P squared star. Okay, so the GL2 FP action on this is given by matrix multiplication on XY. And the FP squared star action on this is given by scaling X and Y in the same way. So it's clear that these two actions commute because this is simply by scaling, which is a central thing inside GL2. Okay, so it should not be obvious why this thing, why you should write down this thing, but it turns out this thing is, okay, actually I won't write that thing, okay. So how do you get representations from this? I'm gonna model it in a similar way to over here, and this thing says, I give you a character of the torus, and I can then hook up for you a representation of GL2. Using this variety here, I can do the same thing. If I take its cohomology, which in this case, kind of all the interesting stuff happens in H1, I'll call this, I'll just call this dash here. This thing, by functoriality of this construction, also will have an action of FP squared star and also GL2 FP. And so that means that if I specify what this action is going to be, then it leaves for me a interesting action of GL2 FP. So I'm going to note this by like this. Okay, so this is often called the Deligne-Lusztig induction of theta, and it's written in the following font, RTG theta. Okay, so natural question is to ask, how does this fit into this picture? And a theorem of Lusztig tells us that if you were to want RTG theta on this side, which you do want, now its class function is not going to look like this. It's going to look like some crazy cohomological thing. However, it turns out that if you do this construction here, all of which still makes sense even for this funny torus, you in fact recover the same thing as over here. So I'll write this equality and this equality. The top equality is easy, the bottom equality is hard, and is due to a lot of work of Lusztig in the 1980s. And I guess, yeah, let's say the 1980s. So any questions about this? So one way to phrase what this means, or what this theorem says, is it says that Deligne-Lusztig induction, geometrically speaking, is simply given by parabolic induction. So I hope this gives you some sense that even though this thing, I mean, that this picture, even though we could just construct it using T, B, and G, this is knowing a lot of information. It knows all the hard representations on this side, for example, not only the easy ones, but the hard ones. So it's kind of parameterizing, it's unifying the picture. Okay, so this I would call the depth zero story. Everything I did, for example, was just on something like GL2 FP. But before I advertised that we should do this for stuff like GL2 FP T mod some higher power of T. And so that's the content. So it turns out that you can do all of this also. So this is a conjecture of Lusztig in 2003 that this picture works if let's say it in this way for jet schemes. Okay, let me tell you what a jet scheme is. I will want to leave that. The jet scheme is a really general construction. Like X being a scheme over FP or FQ, then the R jet scheme XR is defined by the following functor, where for any FP algebra A, XR of A is defined to be X of A, and then you would join T, mod T to the obvious ones. So if you take X0, then you recover the original thing. So this would be like local function field version. There's something that you can do in the QP version, QP world as well. That's via something called the bit ring. Yeah, and so it's one of these two. Okay. If you're happier, it's completely fine to think of it in this, but know that everything I say today works equally well in the two settings. Okay, and so the theorem the paper that appeared maybe 2 months ago. Is it March? Two months ago, is that this the conjecture is true. Okay. So, any questions up to here? Okay, so before I erase all this and tell you about how this conjecture then relates to L packets of positive depth supercuspals, let me tell you a bit about why this conjecture is hard, or why it was hard to obtain this result. So in the characteristic zero setting, this diagram here actually has a famous thing. I mean, maybe this is called a Grothendieck-Springer fibration. And it has analogs in Lie algebra setting, for instance. In the Lie algebra setting, if you put the nilpotent cone here, this gives you a nice resolution of the nilpotent cone. Yeah, so in this setting, if we look at this characteristic zero picture here, the fibers of this map pi are all things that are living inside G mod B. G mod B is a flag variety. This map here is proper. So that means that pi lower straight can think with the pi lower star. But not only is it proper, one can also control the behavior of this map in the sense that the locus on which of GL2 on which the dimension of the fiber is big is actually not so big. Does that mean the size of the stuff inside GL2 where this fiber is large is actually a small locus. And what that means is that one is able to control some geometric vanishing properties of the cohomology of the resulting sheaf. And what we say then is that this thing is a perverse sheaf. Okay, so when Lustig made this conjecture, I mean, the corresponding diagram was really to jetify every single object inside here. So I can put an R here and R here, R. Okay, let me put it like this now. These two maps still make perfect sense. But now this map has very different behavior to before. So for example, the fibers of this map are sitting inside this GR mod BR, which is no longer a flag variety, but it's some kind of a flag variety plus some affine stuff that's stuck to it. But the affine stuff that's stuck to it is kind of changing as the fiber changes. So it's not just like a flag variety times an affine space. That would be great, right? Then everything is solved. So for R, the issue is that this thing is no longer proper. And the effect of that in terms of proving something is perverse is oftentimes if you have this push along something proper, then you kind of only have to prove half of the conditions and the other half are for free because of properness giving you a Schrick star isomorphism. But the other thing that's a problem is that this property about the dimension of the fibers and how many elements in here have large fiber, that is no longer true. And what we call, this is not a small map. It's not semi-small either. And so basically what we had to do in order to obtain this conjecture is to try to find some other way to control this push forward over here. And the way we did this was to introduce some condition on this L theta here. So Lustig's conjecture was not that this picture works in complete generality for jet schemes, but for L theta sufficiently generic. And what we were able to prove is that this sufficiently generic condition basically tells you the following. All the obstructions to this being proper and also small is given by some affine space that's changing as you're moving around your space. And that affine space, the cohomology of that can be controlled if you started with an L theta that was sufficiently generic. So the behavior basically looks like there's some part where everything is as you wish, and you have to make sure that there isn't some extra contribution. And so we use this genericity to prove that there isn't some extra contribution. Okay, so now I'd like to erase all this and then give you a picture of the relationship between this result now and linking back to this and also L packets. Any questions at this point? Yeah.
Like on the Deligne-Lusztig side, do you change something?
Yeah, so that's a great question. Yeah, so on the Deligne-Lusztig side, we also changed something. So over here, it requires you to have a version of this theory for R's everywhere as well. Yeah, and so over here, you're not just going to get depth zero stuff. You're going to get some deeper level version of the Deligne-Lusztig theory. Yeah.
But you recovered that zero.
Yes, you recovered depth zero. Yeah. Yeah, but no, I mean, our proof does not recover the depth zero, Lustig's proof. Our proof just says that for positive depth, you can do the following thing, right? For depth zero, the proof is that this thing is small and proper. I guess maybe in some sense.
In a special case, the map is small and proper.
Yeah, in a
Or
special
hard
case, that,
condition.
yeah. Right, so, okay, so our proof basically goes like this. It says, if you have R positive, then your genericity allows you to work not with the most general derived category, but we're only looking at some generic piece of that. And on this generic piece, we prove that we have an equivalence of categories. That equivalence of categories is going to fail for R equals to 0. That's the sense in which so I think at the end, I will draw a picture that hopefully will clarify the relationship between the positive depth thing and the depth 0 thing. I would really like to think of the positive depth thing as being a way to amplify the depth 0 thing into a positive depth thing rather than replacing depth 0. That you feed in something depth 0 and I will tell you how to get something positive depth from that. Okay, so here's the line of reasoning. Linking generic character sheaves to L packets of positive depth supercuspals. Okay, so my start is I take a t and a theta where t inside G is an elliptic maximal torus. And I will assume that this object is unramified. Okay. And theta is a smooth character. And so the example to think about, or an example to think about, is fp squared GL1 of fp squared prime t sitting inside GL2 of fp prime t, like this. Okay, so from this, what this smoothness tells you is that actually there's only a finite amount of non-triviality to this character theta. Let's say that this character has depth r. And so what this tells me is that this information is captured actually by some object on a jet ski. So I've now taken this kind of infinite dimensional thing into this finite realm. So this is the multiplicative local system corresponding to theta. And what I can do from this is I can take the parabolic induction from BR to TR of this L theta here. And the theorem that I wrote over here is that this is a perverse, irreducible, perverse, GR equivariant sheaf on GR. Oh, this is not T. Okay. And then from this, I can consider its trace of Frobenius. L theta, which gives me a function, a class function on GRFQ or FP. And this thing is equal to the parahoric version of Deligne-Lusztig induction. I have the equation over here. And so the existence of this object is in this jet scheme setting, it's due to Lusztig. In the local function field setting, due to Stasinski, in the QP setting. But actually another lie that I've been telling a bit is that in order to actually get all the supercuspals that we're interested in, it's actually not quite enough to consider jet schemes, these things that look like GR. So we have to expand this class a bit to consider kind of an arbitrary quotient of with respect to the Moivre-Prasad filtration. And so an example of something that can't come as a GR, but we would really like to have this picture for is Iwahori. So Iwahori does not come out as a GR. Okay, so and so in this case of generalizing it to arbitrary parahorics, this is due to myself and Ivanov a few years ago. Okay, so now we know that this thing is equal to this. So now that means that understanding what representations we obtain from this perverse sheaf perverse sheaf technology comes down to trying to understand what this parahoric Deligne-Lusztig induction is. And so that's the next thing. So what it turns out that if you take the compact induction of these R, TR, GR thetas, and now remember that this pair T and theta, this came from the data of an elliptic maximal torus inside my p-adic group. These things can be varied over a natural conjugacy class, but not conjugacy within G, but kind of in G of FP bar. Or sorry, G of QP bar, not just in G of QP. And a construction that people have utilized many times is the sense in which looking at these kind of geometric conjugacy classes traces out for you an L packet. And so that's what I'm going to write down here. So where T theta varies over a stable conjugacy class of such pairs. Okay. Now, so here's something else that you can do. I started with this. This is like an algebraic thing, right? There was no geometry at the start. I could also obtain a family. I'll call this alg to indicate that they're algebraically obtained, such that, and then have this such that be the same. What a natural question then is, you know, are these two the same set? And the really interesting thing is the answer is no. So these kinds of representations were constructed by Adler. That was the maybe second bullet point when I talked about the history. And it was conjectured that this should be an L packet. And what do you have to do in order to prove such a conjecture? Well, you have to prove that the various arithmetic properties of this L packet are true. And it turned out that this L packet, or this set of representations, does not respect stability. In order to get stability, you actually have to twist this algebraic recipe from T theta to pi T theta by a little bit. I'll put this little bit over here. It's not much. This thing is a character that takes values in plus minus 1. So it's kind of like almost there, right? But nevertheless, with this thing is stable, and that's a theorem of de Backer and Spice. And without this, it's false, which is also a theorem of de Backer and Spice. And the really cool thing that I really like is that now these two things are the same. And so what we see here is that the geometry picked up the correct parameterization. So this is joint work with Masao Oi, yeah, so in the last couple of years. Okay, so actually like in terms of chronology, the way I came to this kind of stuff was that I was studying conjecture of Lusztig, and that led, and in all cases where that conjecture is known, the representation theoretic computation comes down to something like this. And so once I had a sense of what this thing was, then I really wanted to know the comparison to something like this. And so then I thought about this. When I saw that these two things match, as in this is the correct parameterization, then there was an obvious next question, is that there should be a way to obtain any of the arithmetic properties of this thing here using the geometry that came over here, right? The geometry knows about the character identities and so forth. And so so in fact, that was the motivation to come to this point. And so now we are at a point where we have a unified way of thinking about these objects. And what I mean by unified is that in order to write down this one, actually you have to write down some variety, and that variety is changing as you change this side over here. However, in terms of perverse sheaves, this object is just the object, like this is the thing, right? And so that gives removes one level of variance that now allows us so the ongoing with Roman and Yakov is to use this in order to obtain character identities for this L packet over here. Okay, so in my last 4 minutes, I'm going to draw a picture, and I will put it here. Okay, so actually, before I draw that picture, let me annotate this thing. So I said maybe 40 minutes ago that the main takeaway of this talk is that the algebraic recipe is geometrically simply parabolic induction. But that is at odds with this statement here. And so actually one has to use algebraic recipe. If you take the modification due to yes, I think I just needed to know which letter came next. Tacho Pleta and Lawrence Weiss. Then this statement is now true. Okay. So let me erase this and tell you R equals 0 versus R positive. So this is this kind of picture is not novel. I think maybe I first learned about this picture in a paper, Computing Characters of Supercuspal Representations by Adler and Spice. So this picture is the picture of GR. This horizontal width tells you, is like this. The middle part is the torus, and let's say like this part is all the positive roots, and this is all the negative roots. And this thing here is telling you depth, how much you need to fatten in. So in the middle is my torus TR, so this is my torus TR. So if I want to write down a levy inside here, that's specifying some subgroup system. And so it's going to be a little bit smaller. It's going to be like this. So let me draw for you what this kind of thing does. Okay, so I have this parabolic induction over here, but actually what I didn't tell you is that our work also works if you replace the letter B by a P, which allows you to not only start with a torus, but with an arbitrary levy. So say I start with an arbitrary levy. This is my, I'll call this levy G upper 0. And I take one of Lusztig's character sheaves on this G upper 0, a depth 0 object. Then what Roman, my recipe tells you is that you can take this thing and then you can tensor it by some kind of easy object in order to get an object on this kind of thing. Okay, so you fattened it a little bit. Okay, then after this, what you can do is you can induce. When you induce, okay, wait, hang on. When you induce, what you're allowed to do? Okay, let's do it. Okay. Here's the thing, because it has some depth, it may not be the full depth. So that's what this thing will be. I'm going to induce, and by our equivalence, you still get something that's irreducible and perverse. Okay, after this, I'm allowed to tensor up by some kind of generic thing with respect to the next thing, and then induce again. And then you do this again. Tensor, induce. tensor, induce, until you get everything. So we're not really, the intention is not to replace the depth zero theory of character sheaves, but it's to give you a machine in which you can input that thing and then get like output arbitrary positive depth equivariant perverse sheaves. So I'll stop there. Yeah, thank you.